Hey guys, this is Mrs. Lyons, and this video is going to walk you through the idea of half-life and the kinds of questions you might see regarding half-life. So first of all, we need to define half-life. So what half-life is, it is the amount of time required for 1/2 of a radioactive element to decay. Okay, so basically what we're saying is if you have 100 grams of a radioactive substance, after a certain amount of time it undergoes decay, and when it gets down to 50 grams, that's half of 100, that whatever time that is would be the half-life. And it turns out that half-lives can range from anywhere to seconds to thousands of years. Okay, so if you look at this graph, this is a graph you might see if you were looking at half-life. Okay, so if you're looking at this, if you see, we're measuring atoms. So we start up here with 80 atoms. Okay, so 80 atoms. And then we want to figure out how long is the half-life. Okay, so the half-life would be however much time it takes to end up with 40 atoms. Okay, so if I look at my graph, here is 40, and I go down, that is 2 days. So a half-life is 2 days. Okay, so in 2 days, if I started with 80 atoms, after 2 days I would have 40 left. Okay, so this next question says how many atoms are left after 2 half-lives. Okay, so 2 half-lives would be 2 days plus 2 days. So 2 half-lives would be 4 days. So 1, 2, 3, 4. If you look, after 4 days, 20 atoms would be left. All right, and then just in reading the graph, how many atoms are left after 6 days? So we'll read across to 6 days, and that would be 10 atoms. Okay, so that's kind of the idea as we look at these questions about half-lives and looking at graphs. So let's look at another graph. Okay, so what is the half-life of the substance in the graph? So when you look at this, the important thing is to look at what you start with. So in this graph, we start with 16,000 isotopes. All right, so 16,000, what's half of 16,000? 16,000 divided by 2 would be 8,000, right? So the half-life would be the time it takes to get down to only 8,000 atoms left. So if I plot that point on the graph and go down, that is going to be 8 days. So the half-life of this substance is 8 days. How much of the sample will remain after 1 half-life? 8,000. We're going to say atoms. Okay. The time required for 2 half-lives to pass. Okay, so if 1 half-life is 8 days, 2 half-lives would be 16 days. How much of the sample is left after 2 half-lives? So I'm going to look at 16 days. I'm going to go up here. 4,000 atoms would be left. And then what is the amount of time required for 3 half-lives to pass? Okay, so if 1 half-life is 8 days, 2 is 16. 3 times 8 is 24 days. All right, and then it says how much of the sample will remain after 3 half-lives. So I look at my graph, I go to 24 days, and I see that 2,000 atoms would remain. Okay, so that's how we would do this, looking at a graph, okay? Oftentimes, though, what you're going to see is a word problem, okay? So you would see something like this. Molybdenum 99 has a half-life of 66 hours. What percent of a sample is going to remain after 198 hours? Okay, so here's the way that I suggest looking at this. Okay, so we're looking at the number of half-lives, the amount of time, and the amount of excuse me, the amount of material. And sometimes we'll give you the amount of a material in grams, or in atoms, or in this case, a percent. Okay, so let's just kind of see how this works. Okay, so at time 0, okay, so before we start figuring out our problem, okay, at 0 half-lives, 0 time, the amount of the material that's left, in this case it says what percent. So when we're talking about percents, the amount of material would just be 100%, okay? So then after 1 half-life, and it tells us the half-life is 66 hours, how much substance would be left? Okay, if we start with 100%, half of that would be 50%. Okay, then we go after 2 half-lives. I'm going to grab my calculator so that I don't make a math mistake. Let's see, calculator. So I need to do 66 plus 66. So 2 half-lives is going to be 132 hours. Okay, and after 2 half-lives, half of 50, so 25% of the sample remains. Now, what we're trying to get to 198 hours. Okay, so after 3 half-lives, I'm going to do 132 plus 66. There we go. That's 198 hours. All right. How much would be left? I take 25% divided by 2, so 12.5%. Okay, so this tells us that 12.5% of our sample would be left after 100. All right, let's look at this next question. This next question says, indium 111 has a half-life of 2.8. Whoops, I'm out of focus. There we go. Indium 111 has a half-life of 2.83 days. What percent will remain after 11.32 days? So again, I'm going to set this up. Number of half-lives, amount of time, and the amount of our sample. All right. So if we think about this, all right, at time 0, all right, so 0 half-lives times 0, we have 100% of our sample. All right. After 1 half-life, so what is our half-life? Our half-life is 2.83 days. Okay, we would be down to 50% of our sample. All right. After 2 half-lives, I've got to double this, so 2.83 plus 2.83 is 5.66 days. I would now be down to 25% of my sample. All right. After 3 half-lives, I'm going to take 5.66, add 2.83. I'm going to add 1 more half-life. That would be 8.49 days. Okay, and then 25 divided by 2 would be 12.5%. Okay, so we're still not there. We're trying to get to 11.32 days. So after 4 half-lives, I'm going to take 8.49 and add 1 half-life, so plus 2.83. There we go. I get to 11.32 days. Okay, and 12.5 divided by 2, I would use my calculator because sometimes you make silly mistakes. So 6.25% of the sample remains. Okay, so that's the way that you're going to go about solving these problems. Okay, so let's look at the next one. All right, the next one says you have 125 grams of phosphorus 33. The half-life is 25.4 days. How much phosphorus remains after 2 half-lives have passed? Okay, so I'm going to set this up. Number of half-lives, time, and amount of material. Okay. So at time 0, what does it say? We have 125 grams. Now, notice what it says. It doesn't really ask us how much time is needed, but we could go ahead and work the problem just like we have been. It's not going to hurt anything even if we get some extra information. So after 1 half-life, okay, 25.4 days, we end up with, what is 125 divided by 2 is 62.5 grams. All right. This is saying after 2 half-lives. So after a second half-life, I'm going to take 25.4 plus 25.4, so 50.8 days. And then half, I'm going to take 62.5 divided by 2, gives me 31.25 grams. So after 2 half-lives, I'm going to have 31.25 grams left. Okay, now here's the thing I want you to notice here, okay? We didn't need the amount of time, okay? It gave us 2 half-lives. It doesn't say how many days or how many years. So we have some extra information. So when you answer these kind of problems, you've got to make sure that you look at what the question is asking. Okay, I go through this kind of process every time just because it gives me everything I need and I don't have to kind of think about which way to answer the question. All right, so let's look at number 14. All right, so half-lives, I'm going to abbreviate. Every time I abbreviate a little bit more. Number of half-lives, time, and amount. All right, at time 0, what does it say? I have 510 grams of material. And so 510 is what I start with. The half-life is 5,790 years. All right. And it's asking us how much carbon-14 remains after 3 half-lives. So that tells me I'm going to have to do my graph out to 3 half-lives. Okay, so the half-life is 5,790 years. Okay, so after 1 half-life, we would have to take 510 divided by 2 is 255 grams after 1 half-life. All right, I'm just going to, while I've got this on my calculator, I'm going to divide 255 by 2 again. That gives me 127.5 grams. And I'm going to divide that by 2. That gives me 63.75 grams. Now, if I want to, I can actually figure out the amount of time. So 5,790 plus 5,790, that would be 2 half-lives. 11,580. And if I wanted the amount of time, now I'm going to add another 5,790. That gives me 17,370 years. Now, did I need that? No, I didn't need it because it's asking me how much remains. So after 3 half-lives, 63.75 grams remains. Again, I didn't need the time at all, but it's just kind of my process. I want to make sure that when I get done with the problem, I have whatever it is I need. And it's easier than trying to think about which way to solve this. All right, let's look at number 15. Krypton 81 has a half-life of 13 seconds. Okay, big difference, right? 5,790 years for carbon 14, 13 seconds for Krypton 81. So half-lives can be kind of all over the place. All right, so how long does it take for 400 grams to decay to 50 grams? Okay, so let's set this up. We've got number of half-lives. We've got time. And we've got amount. All right, and this one is a little bit different, okay? It's saying, it's a little bit different, but again, we think about it the same way. So we start at time 0, 0 half-lives, and we start with 400 grams. All right, and then it asks us, how long would it take for 400 grams to decay to 50? Okay, so what we're looking for is, if I want to do the amount first, if I start with 400 grams, oops, so if I start with 400 grams and I divide by 2, that's 200 grams. If I divide by 2 again, that's 100 grams. And if I divide by 2 again, that gives me 50 grams. Okay, so I've gotten from 400 to 50 grams. How many half-lives did that take? Well, 1, 2, 3 half-lives. All right, so I could really, if I wanted to solve this, I could just take 3 times 13. I'm going to work it all the way out. So 13 seconds, 13 plus 13 would be 26 seconds. That would be how long it took for 2 half-lives. And then 26 plus 13 is 39 seconds. Okay, so it does actually ask me how long does it take. So the time is going to be 39 seconds for 400 grams to decay to 50 grams. All right, we've got 3 more questions. All right, hopefully this is just kind of, it's a process, and if you can figure out the process, you will not have any problem with any of these types of calculations. All right, number 16. Strontium 89 has a half-life of 50.5 days. How long does it take for 30 grams to decay to 7.5 grams? So another problem kind of like the one we just did above. Okay, so I'm going to set up my table, number of half-lives, time, whoops, and amount. So at time 0, what do I start with? I start with 30 grams. And I need to get down to 7.5 grams. So I need to, let's figure that out first. So 30 divided by 2 is 15. 15 divided by 2 is 7.5. That's what we're looking for. Okay, so this tells us it's going to be 2 half-lives. Okay, now how much time? 1 half-life is 50.5 days. So 2 half-lives would be 50.5 plus 50.5. 101 days would be how long 2 half-lives is. So our answer is going to be 101 days. Okay, all right, next. Number 17, the half-life of technetium-99 is 213,000 years. If the original mass is 214 grams, what is the remaining mass of technetium after 639,000 years? Okay, so let's set up our table. Half-lives, time, amount. All right, so at time 0, okay, we start with 214 grams, and this is saying after 639,000 years, so we've got to kind of figure out, so one half-life is 213,000 years, okay, so that's one half-life. And after one half-life, we're going to take 214 divided by 2. We would have 107 grams left. Okay? After two half-lives, how much would we have left? I'm going to go ahead and divide, since I've already got my number here. Divided by 2 is 53.5 grams. And I'm not sure how many half-lives I'm going to need, but I'm going to divide by 2 one more time. So if I would go to my third half-life, I would have 26.75 grams left. So let's see if that gets us where we need to be. So that would be after 3 half-lives. So 2 half-lives would be 213 times 2, which is 426,000 years. All right. What is 3 half-lives? 213,000 times 3 is, oh, check it out, 639,000 years. Okay, so what that says is after 639,000 years, 26.75 grams would remain. All right, let's look at one more problem. The half-life of indium-129 is 15,700,000 years. These are actual numbers. When I made this problem set, I actually looked up. So indium-129, literally for half of it to decompose takes 15 million years. That's why uranium, which is radioactive substance that is used in bombs and nuclear power plants, that's part of the problem with it, is because it lasts so long and that it's dangerous for that whole time. All right, so let's set this up. If the original mass is 550 grams, what is the remaining mass after 62,800,000 years? All right, so half-lives, time, amount. So at time 0, what do we start with? 550 grams. All right, and then one half-life is 15,700,000 years. All right, so let's see. It's giving us a number of years. So let's see if we can figure out how many half-lives. So let's see. So 15,700,000 years times 2 is 31,400,000. Okay, you could also, a quicker way to do this is, if you wanted, you could have 62,800,000 divided by 15,700, and that's 4 half-lives. So that tells us we don't have to go on to that 5th half-life. So I'm going to put this out here, but I'm going to go ahead and fill out my table just because. All right, so 31,400, 31 million, oh my goodness. And we're going to add another half-life, so 15,700, there we go, is 47 100,000. Then I'm going to add one more half-life plus 15,700,000. Oops, I put that in the wrong place. 62,800,000 is 4 half-lives. Okay, so now all we have to do is take our beginning, what we started with, so 550 grams divided by 2 is 275 grams, divided by 2 is 137.5 grams, divided by 2 is 68.75 grams, and we don't need this fifth one, and then divided by 2 is 34.375 grams. So after 4 half-lives, 68 million years, we would still have 34.375 grams of that material remaining. Okay, so this is, just a quick video for you to look at to explain how to approach those half-life problems. And if you noticed what I did, no matter what the question was asking, I could always find out what I needed by creating this table. So rather than figuring out how to read each question and figure out exactly what each question is asking, because they're all a little bit different, if you set up this table and you just kind of go through that process, you're going to get to the right answer in the end. Okay? So I hope that this was helpful, and I will see you in class. Have a great day.